The interpretation of entropy in statistical mechanics is the measure of disorder. An isolated system has higher probability to become more disordered over time. So, the entropy of isolated system always increases. It is in accordance with the Planck statement of the second law of thermodynamics. To understand this principle, let's use a room as an example. At the beginning, the room is highly ordered. However, after living without tidying, it becomes disordered. We can say that the entropy of the isolated room increases over time. The room can return ordered again, but some work or heat must be involved, and the room is no longer isolated. For a given macro state, the entropy measures the degree to which the probability of the system is spread out over different possible microstates. Boltzmann gave his formula of entropy as follows. Here, Kb is Boltzmann constant. Omega is the number of possible microstates in the system given a certain macro state. The bigger the number of microstates is, the more disordered the system is, and the higher the entropy is. For example, suppose there are 2 red boxes, 2 blue boxes, and 2 indistinguishable balls. If the macro state is that both the balls are in the red boxes, there is only one possible microstate. If the macro state is that the balls are randomly distributed into the boxes, there are 6 microstates. The later macro state is more disordered than the previous one and has a higher entropy. This example is an analogy of free expansion. Consider, if the balls are distinguishable, how about the numbers of microstates? The third law of thermodynamics states that the entropy of a perfect crystal at absolute zero is exactly equal to zero. The alignment of particles in a perfect crystal leaves no disorder in their equilibrium positions. At absolute zero, the vibrations of the individual atoms are reduced to nothing. The electrons also freeze to their ground states. Thus, there is only one microstate and the entropy is zero. The third law of thermodynamics provides an absolute reference point for the determination of entropy at any other temperature. The absolute entropy of a substance at a certain pressure is the integral of ds with respect to temperature from absolute zero to the target temperature. It can be calculated if Cp is known. However, at a phase transition, the temperature is constant, while the heat is a finite value. So, Cp at phase transition is infinity, and the integral cannot be calculated. Nevertheless, the entropy of the phase transition is surprisingly easy to measure and calculate. It is the heat of the phase transition divided by the phase transition temperature. The heat of phase transition is also called latent heat, as the temperature is a constant. The molar absolute entropy of a pure substance is called its standard molar entropy. Here is an example of standard molar entropy of nitrogen at 1 bar. At absolute zero, the entropy is zero. The entropy increases with temperature. At phase transitions such as transition between solid phases, fusion and vaporization, the entropy increases without the change of temperature. We can qualitatively analyze the relative entropies of a substance in different states using their degrees of disorder. For example, the particles in the solid can hardly move except vibrate slightly near their equilibrium positions. So, a substance in the solid state is the most ordered and has the lowest entropy. In liquid state, the particles can rotate and translate slowly. So, a substance in liquid state is less ordered and has higher entropy than it in solid state. In gas state, the particles can freely translate, rotate, and vibrate. So, a substance in gas state is the least ordered and has the highest entropy. The tendency of entropy can be understood thermodynamically as well. The fusion and vaporization are accompanied by positive heat. So, the entropies increase from solid to liquid and gas. The entropy increases with temperature. It is because at higher temperature, the particles have higher energy to move, so the system is more disordered. It can be understood thermodynamically as well. The heat capacity is always positive. When molecules are mixed, the entropy increases. It is because the particles in the mixture have more space to move, and the system is more disordered. The reaction which increases the number of molecules usually increases the entropy. It is because the particles in separate molecules usually have higher degree of freedom in motion than those in combined molecules. For a general reaction, the standard entropy of reaction is the difference between the standard molar entropies of the products and the reactants. Let's have a look at a special example of the decomposition of mercury oxide. The standard entropy of this reaction is very positive. It is because the reaction increases the amount of gas, which has high entropy. In another example, the decomposition of mercury sulfide to mercury and sulfur also has a positive standard entropy of reaction. However, since all the products are in condensed states, the entropy increase is much less. Finally, let's have a look at the combustion of graphite in oxygen to form carbon dioxide. At the first glance, it seems that the number of molecules decreases, so the entropy should decrease. However, the entropy increases slightly. That is because graphite is a solid. Its contribution to entropy change is very small comparing to oxygen and carbon dioxide. On the other hand, carbon dioxide has more degrees of freedom in vibration. As a result, the overall entropy change is positive.